Right now, somewhere in the world, a rocket is launching into orbit. A surgeon is performing a procedure guided by an AI system. A self-driving car is reading the road at 120 kilometers per hour, and all of them are powered by chemistry that a man in the 1800s figured out with copper discs and wet cloth. We live in an age of miracles, but the thing that powers almost all of them hasn't fundamentally changed in nearly 2 centuries. So, is that a failure of science? Or is it a sign that someone a very long time ago got something profoundly right? In this video, we're going to answer some questions that most people never ask. Like, who actually invented the first battery, and was it really an accident? Why does your phone battery get weaker every year? And is that really unavoidable? What happens inside a battery when it's giving your device power? And why does it eventually stop? Are lithium batteries actually dangerous? Or is that just a myth? And the big one, what comes after lithium? Is there a next generation already waiting? Stay with us. This is going to be a calm ride, but by the end, you'll never look at a battery the same way again. Now, how many of these did you already know? Drop it in the comments. I genuinely want to find out. And if you're new here, don't forget to like the video and subscribe to the channel. Welcome to the Midnight Engineer. It all started with a dead frog. In the late 1700s, an Italian scientist named Luigi Galvani noticed something strange. When he touched a frog's leg with 2 different metals at the same time, the leg moved. He thought electricity was coming from the frog. He called it animal electricity. He was wrong, but beautifully wrong. Another Italian, Alessandro Volta, disagreed. He believed the electricity was coming from the metals, not the animal. So he tested it. In 1799, Volta stacked zinc and copper discs with wet cloth between them, and it worked. It produced a steady electric current. He called it the voltaic pile, the world's first real battery. And here's the part that should surprise you. The core idea behind Volta's pile is still inside the battery you charged last night. 2 different metals, a substance in between, a chemical reaction that pushes electrons from one side to the other. That's it. That's a battery. 200 years later, we made it smaller, safer, and more powerful. But the principle, almost the same. So what actually happens inside a modern battery? Think of it like a very organized crowd. On one side, you have the anode. This is where the energy is stored. On the other side, the cathode. This is where the energy wants to go. Between them, there's a liquid or gel called the electrolyte. It's like a hallway that only lets certain particles through. When you use your phone, tiny particles called lithium-ions start moving through that hallway, from the anode to the cathode. That movement creates the electric current that powers your screen, your camera, your apps. When you plug in your charger, you're pushing those particles back the other way. That's charging. Simple in theory. But in reality, every single time those particles move back and forth, they cause tiny amounts of damage inside the battery. The hallway gets a little narrower. The anode changes shape slightly. Small crystals form where they shouldn't. After hundreds of cycles, your battery holds less charge than it used to. That's not a bug. That's chemistry. Here's a question almost everyone has asked. Why does my phone battery get weaker every year? And the answer is both simple and a little frustrating. Every time you charge and discharge your battery, the materials inside change. Just a little bit. Tiny and permanent. Heat makes it worse. Charging to 100% every night makes it worse. Letting it drop to 0% makes it worse. Most lithium batteries are designed for around 300 to 500 full charge cycles before you start noticing a real difference. Some high-quality ones go up to 1,000. After that, they don't die. They just shrink. less capacity, shorter days between charges. And here's the uncomfortable truth. This is partly by design, not in a conspiracy kind of way, but because the materials that last longer are also more expensive, heavier, or harder to manufacture. The battery inside your phone is a compromise between cost, weight, safety, and lifespan. The question is, can we do better? You've probably heard the stories. Phones catching fire on planes, laptops overheating, electric cars with battery problems. So, are lithium batteries dangerous? The honest answer is, they can be, but usually only when something goes very wrong. Lithium batteries store a lot of energy in a small space. That's exactly what makes them useful, and what makes them risky if they're damaged, overheated, or poorly made. There's a process called thermal runaway. If one cell inside a battery gets too hot, it can trigger the cells next to it, and it can escalate very quickly. But modern batteries have multiple layers of protection. Software that monitors temperature, physical separators, circuit breakers, which is what we call battery management systems. The batteries that fail are usually ones that were damaged, cheaply made, or pushed far beyond their limits. Your everyday phone battery, the risk is very low, but it's not zero. And that's exactly why researchers are working hard on what comes next. This is the part where things get exciting. The world right now runs on lithium-ion, but there are at least 4 serious candidates to replace or improve it, and some of them are already leaving the lab. Solid-state batteries. Remember the liquid hallway inside a lithium battery? What if you replaced it with a solid material? That's a solid-state battery. No liquid means no leaking, much harder to catch fire, and potentially much more energy in the same size. Toyota has been promising solid-state batteries in cars by 2027. Whether that happens on time, we'll see. But the progress is real. Sodium-ion batteries. Lithium is actually not that common. It's mostly found in a few countries, and the price goes up and down. Sodium is everywhere. It's basically salt. Sodium-ion batteries use the same basic idea as lithium-ion, but with a material that's much cheaper and easier to find. They store a bit less energy. But for things like home power storage or city buses, that might not matter. Lithium-sulfur batteries. Sulfur is incredibly cheap, and in theory, lithium-sulfur batteries can store up to 5 times more energy than today's lithium-ion. The problem? They break down fast. After a few dozen cycles, they lose capacity quickly. Researchers are working on this. It hasn't been solved yet, but when it is, it could change everything. Silicate anodase. This one is closer than you think. Today's batteries use graphite on the anode side. Silicon can hold much more lithium, nearly 10 times more, but silicon expands when it absorbs lithium ions. It cracks, it breaks. Some companies are already using small amounts of silicon in their anodes, finding a balance between more capacity and less cracking. This might be the first upgrade that actually reaches your phone in the next few years. Here's why this all matters beyond just your phone. The world is trying to move away from fossil fuels. Solar panels and wind turbines are getting cheaper every year, but they have one big problem. The sun doesn't always shine. The wind doesn't always blow. To use clean energy all the time, we need to store it, and that means batteries. Huge ones, city-sized ones. Today's lithium-ion batteries can do this, but they're expensive. They degrade over time, and lithium isn't available everywhere in the world. The next generation of batteries isn't just about your phone lasting longer. It's about whether clean energy can actually work at a global scale. That's a much bigger goal. And it's why some of the smartest people in science and engineering right now are working on batteries. Not rockets, not AI, batteries. Because the future of energy might depend on solving a problem that started with a dead frog in 1799. So, we went from a frog's leg in 18th century Italy to solid-state batteries that might power your car in 2027. The chemistry changed, the materials changed, the scale changed. But that core idea, two different materials, something in between, electrons moving from one side to the other, that's been with us for over 200 years. Maybe the next 200 years will finally change it. Or maybe the real breakthrough is much closer than we think. Now, what about you? What did you already know about how batteries work? Please write it in the comments below. Welcome to the Midnight Engineer. Please don't forget to like the video and subscribe to the channel. We'll see you in the next one.